Hey everyone, in this episode of the Geek Narrator podcast, we'll talk to Ayush from Blacksmith about the challenges of continuous integration and how Blacksmith addresses these issues by providing serverless compute for GitHub Actions. We'll also discuss the importance of optimizing CI workloads, the user journey of integrating Blacksmith, and the technical innovations that allow for instant compute availability. Ayush explains the unique advantages of using gaming CPUs and the optimizations made for file systems to enhance CI performance. In this conversation, we'll discuss the evolving landscape of consumer desktop performance, particularly focusing on single core performance and its implications for CI workload. The discussion also covers the optimization of CI infrastructure using Firecracker. Yes, one more time, Firecracker. The challenges of flakiness in CI systems. I'm pretty sure you all have faced flakiness in the systems, and it's pretty painful. And also the importance of observability. So let's dive right into the episode. It is extremely insightful. If you have ever used GitHub Actions or faced problems with CI pipelines or are just interested into learning about general systems engineering topics, this is an episode for you. I hope you like it. Before you go and enjoy the episode, please subscribe to the channel if you haven't yet, and also like if you like this episode and share it with your friends. Now, enjoy the episode. Hello, everyone, and welcome to another episode of the Geek Narrator podcast. I am your host, Kaivalya Apte, and today we have a very special episode because it's a different topic that we haven't really covered on any of the episodes in the podcast. So we are going to talk about Blacksmith, and to do that, I have Ayush with me from Blacksmith, and we'll dive deep into how it works, how you can use it, and when you can use it. So welcome, Ayush. I'm really excited to have you here. Let's start with an introduction about yourself, what you've been doing these days, and a little bit about Blacksmith.
Cool. Thanks for having me. A bit of background on me. I started my career working on distributed databases. Right out of college, joined Cockroach Labs, working on Cockroach DB. Spent about 3 years there. I worked on a lot of subsystems in Cockroach that relate to the transaction layer, as well as sort of Cockroach DB's data placement and data co-location subsystems. And after that, I spent a little bit of time at a company called Superblocks, which is a platform to build internal tools for enterprises. At both of these jobs and across my internships, me and my co-founders, we felt like writing code was often only kind of half the battle. It was often much harder to get your changes merged in, and that was not primarily because of code review reasons or organizational reasons. They were typically due to slow CI, but more importantly, like flaky CI. And I feel like that trend has only accelerated with code gen tools, making it much easier to write a lot of code. And in some cases, write a lot of code that maybe isn't the most well thought out. And that's sort of the meta reason we got interested in CI as a space, because it felt like it was this ignored, like unsexy part of infra that no company really wants to manage yet. Once they get to a certain size, once they get to beyond 20 or 30 engineers, it starts becoming a real bottleneck. A little bit about Blacksmith is that we provide serverless compute for CI. Our first offering provides compute and observability for GitHub Actions, which is GitHub's CI system. I'd say today it's the most popular CI system and it's the fastest growing one, just because most projects being started today are on GitHub. GitHub Actions is sort of well integrated into GitHub, comes out of the box in any repository. You just have to add GitHub's DSL file and you have GitHub Actions. And Blacksmith provides sort of very instantly provisioned compute for GitHub Actions that runs on bare metal gaming CPUs. So that's kind of one of our differentiated takes into the space. And on top of that, Blacksmith has a lot of optimizations that you would want to make for CI workloads, but not necessarily for production workloads. I'm happy to kind of dive into both of these points.
Yeah, thanks for the introduction. I mean, there are so many things that you mentioned. I can totally relate to it, right? And as you said, it's like this unsexy area. I mean, there are problems, but no one really wants to solve those problems. Everyone faces them like every day, but from the ground up, no one is actually solving the problem. There are still optimizations, at the pipelines level, and how you can run your code or build your code and test your code and all of that, but not within the CI space. The other thing that you mentioned was about instantaneously making compute available, and I can imagine how big of a challenge that is. So I would love to go deeper into that. You also mentioned gaming CPUs, right? And so all of these are really interesting areas I would love to dive deep into. You also mentioned serverless solution, right? So I want to start there and understand why serverless makes sense for a workload like CI.
Yeah. So I think the interesting thing about CI as a class of workloads is that CI is what I would call extremely sparse, but extremely bursty. Consider the case of, one of our customers has a test suite with 40 shards of tests. They run a large, jest test suite. Each of these 40 shards is heavy enough that they need to run it on 16 vCPU VMs, 16 vCPU instances. So on every Git push, they effectively need, on the order of 5 to 600 vCPUs. Every time a developer does a Git push, 5 to 600 vCPUs need to be provisioned for the test suite to even begin. Peak business hours, we'll see their workload spike from using 0 vCPUs 1 minute, and then in another minute, spike up to 3,000 vCPUs across the org. One of our initial realizations with Blacksmith when we were looking into the space was that traditional hyperscalers like GCP, AWS, Azure are simply not meant for such workloads. In other words, they don't necessarily have a compute primitive that you can run CI on and is also sort of instantly provisionable. Hyperscalers, obviously have AWS Lambda and the serverless equivalents, but those are not full VMs. They come with a pre-baked runtime. You can tell AWS to run your TypeScript Lambda function. It'll go, run it on some trigger. And they have, full baked EC2 instances or ECS or Fargate containers, but those are not guaranteed to be provisionable in 3 seconds. So what this customer, the core pain point they had was for their test suite to even begin, for them to get, 40 V instances of capacity for each Git push would take on the order of 5 to 10 minutes. And it would be higher during peak business hours because that's when everyone else's on-demand workloads are also sort of spiking, right? So we realized that there's probably a gap in the market around providing compute out of a pool of compute where the only class of workloads you're running are CI workloads. The reason this ends up mattering is CI workloads in general have a much smoother sort of usage curve across a large set of customers. Within each customer, it'll be very spiky and bursty because if you have 40 engineers, chances that 3 or 4 of them are Git pushing at the same time are relatively low. But when you're providing compute for a pool of 100,000 engineers, the usage curve actually looks a lot smoother. And because CI workloads don't have externalities that kind of affect their demand, as in CI workloads are not affected by the fact that folks are ordering lunch at lunchtime. They sort of just follow a business day pattern. Developers in the US, in the Eastern time zones will generally push code at a uniformly distributed rate in that window of time, so on and so forth for all these different time zones. Yeah, so that's kind of where the genesis of this serverless idea comes from. We actually felt like CI was one of the workloads where the serverless usage pattern makes the most sense from the perspective of a customer, just because of how sparse the workloads are and how bursty they are.
Interesting. So I think 2 points, right? When there is no traffic, no CI thing going on, you can take down, you don't have to pay for the resources. And suddenly, if you have peak, the instantaneous compute will help you because you can scale immediately. That's fair enough. I want to actually, before we dive deep into, each of these things, how it works, I want to start from the user, right? So let's say I'm already using GitHub Actions for my workloads, and I have this pain my pipelines are slow and everything is just too slow. I have to wait longer. I cannot make hot patches in my production when there are bugs and so on. So I want to evaluate some new tools. I discover Blacksmith and I want to use it. So what is the journey like? And from the user's perspective, what do they have to change? What does change mean for them? And then we can take it from there and, go deep into how Blacksmith works.
Yeah, that's a good question. So one of the core product principles we have at Blacksmith is everything we do needs to have as low of a time to value as possible. So to get set up with Blacksmith is extremely simple. You install our GitHub app, which gives us event notifications for your GitHub repo, as in when new jobs are queued up, we get a webhook from GitHub. And it also gives us permissions to run your CI jobs. So all you have to do is install our GitHub app. And for the jobs that you want to run on Blacksmith, you just change the compute label on that job to point to Blacksmith instead of GitHub's default runners. And that's pretty much it. And the moment you do that, not only do you get this like instantly provisioned compute, you also get out of the box observability into the CI pipelines that you're running on Blacksmith. So it will help you track over time which pipelines have regressed, what is the P50 over some window of time, what are like the cache hit ratios on your Docker builds over some window of time. So let's say someone makes a change to one of their Docker files that affects their Docker build times. You'll be able to track that much more easily with Blacksmith. And in terms of the user's experience before and after being on a system like Blacksmith, the main difference is that your hotfixes don't have to wait for compute to be available for the jobs to even begin. This is a problem that not many developers notice at smaller organizations, but as you get to like a larger company that needs these like high bursts of compute, this increasingly becomes a problem. And another pain point that we sort of instantly solve for our customers is eliminating flaky tests that are due to IO bottlenecks on compute. This kind of leads into another big point behind our thesis. Traditional hyperscalers effectively force bundle network attached storage with their instances. So for instance, on AWS, getting a C7 instance with an EBS volume is substantially cheaper than getting the same instance type with a local SSD. And the difference in IO performance, IOPS, across these two instance types is actually quite massive. Getting an EBS volume that only lets you do 10,000 IOPS is substantially more expensive than just getting a local SSD instance on the hyperscalers and just like the actual cost of the hardware itself. But we realized that first you actually need like the highest performing disks as possible, and you actually don't care about durability, because a typical CI pipeline performing a Docker build or building a large Rust or a Golang project is typically reading and writing a lot of source files, a lot of object files, performing linking in a separate step. All of these things are fairly IO bound, and the state is sort of entirely ephemeral. When you build a build artifact in CI, a Docker image that's like published to the Docker registry, no other state in your VM that was running the CI job is actually persisted. Like it's all sort of ephemeral state to begin with. So we realized that the fact that hyperscalers force bundle you into network attached storage was also a big drawback of running CI on GitHub, which is sort of just like wrapped around Azure VM primitives, or even self-hosting CI on AWS or GCP.
Okay. That's a good point. Yeah, I mean, most of the work that these CI things do, they just get data from somewhere, do some processing and submit some results, right? But they don't necessarily need to persist data. So even if a pipeline fails, it can restart, it can reload the data and all of that. So that makes sense. From the user's perspective, you mentioned that, so two steps, right? Like you need to install, let's say, the GitHub application, and then you need to change the label of the compute and change it to Blacksmith's label, and it will work. What is the role of the app here?
So I'd say mainly two things. One, it gives us event notifications for when we need to spin up VMs to process CI jobs for the org. So for the example that I was just talking about, so for this, hypothetical customer, when someone does a Git push, we would get, 40 different event notifications from GitHub to spin up VMs for those 40 CI jobs. Blacksmith would then spin up those VMs, and we can go into how all of that works. And Blacksmith will hot load all of your Docker layer caches, a bunch of caching primitives into the VMs themselves, and then it will request permissions to actually execute the job from GitHub's control plane. So the GitHub app lets us authenticate with GitHub and just prove that we're allowed to execute these jobs.
Interesting. That's a good point. And now I understand this workflow. Okay, so let's take the next step, right? Like I am using a GitHub app, and I also change the label, and now I make git push, and that will trigger my pipeline, and it has like a bunch of steps, like I don't know, testing, building the code, and probably deploying it, running another test suite, and so on. What kind of events do you get from GitHub, and how do you make the compute immediately possible?
That's a good question. I'll start with sort of the second part of your question. How do we make the compute instantly available? Because that's kind of the one of the key reasons you would want to consider using something like Blacksmith. So as I said before, we manage our own pool of hardware. We manage our own pool of bare metal gaming CPUs. I'd like to go into why we went with consumer desktop gaming CPUs as opposed to server hardware. Over this fleet of bare metal hardware, we orchestrate Firecracker VMs. So for those who don't know, Firecracker is this hypervisor built by AWS. It underpins two key technologies for AWS. One is Lambda and the other is Fargate. So Fargate containers are effectively Docker containers running on Firecracker VMs. One of the key reasons to use something like Firecracker is extremely fast cold start times on the VMs. So for context, the Firecracker runtime itself adds effectively no overhead in terms of starting the VM. I'd say within 100 to 200 milliseconds, we're already booting into the VM. And then because we run a fairly beefy file system or operating system image, that takes another 2 to 3 seconds. So within 3 seconds, you kind of have like a fully fledged VM that's ready to start running the customer CI jobs. So going back to the event notifications that we get from GitHub, we figure out which machine in our fleet has like the best characteristics to run this particular CI job. So for instance, if a job requires 64 gigs of RAM, 16 vCPUs, we figure out which of our machines is like the optimal candidate to adopt that job. Once we figure that out, that machine starts setting up a few things to be able to run the VM. The first is it sets up a copy on write clone of the file system image that we use to run these CI jobs. The intuition behind this is that these file system images are on the order of 70 to 80 gigs. So they're pretty massive. They have a bunch of popular runtime dependencies like your common node versions and your common JDK versions and a bunch of systemd services that run in the background in the VM. It's effectively a full Ubuntu 2404 or Ubuntu 2204 image. But because these images are so large, copying them for every job execution is simply not feasible. Like if you were to try to copy 70 gigs of data for each VM, for the VM to have its own mutable state, that would take us on the order of minutes to provision these VMs. So effectively, we create these copy on write clones. We used to use this file system called ZFS, which allows like native copy on write cloning of file systems. And now we've moved to a slightly more like bespoke system. But once the file system is set up, we'll set up networking for the VM to run in its own network namespace. And for all ingress traffic to the VM or ingress and egress traffic for the VM to flow through its own subnet. And yeah, like that, those are kind of the main components. We set up the networking, we set up the disk, and then we boot into the VM and ask GitHub to give us the permissions to start executing the job.
Interesting, very interesting. And it's so cool that you mentioned Firecracker again, because I just did podcast episode on Lambda, and there was Firecracker. I did an episode on DSQL, that is the Aurora DSQL, new distributed SQL offering that also used Firecracker. So I guess Firecracker is an important piece wherever you want to spin up your VMs quickly in a lightweight manner. I think Firecracker is a game-changing thing. And so I'll attach the necessary links so you can check out what Firecracker is, read more about it if you're curious. But that's really interesting, right? So Firecracker gives you this ability to quickly spin up compute. You mentioned a few things there, and I want to understand each of them. You mentioned about configuring a file system. Why do we need a file system? Like we just talked about, we don't really need durability. So I want to understand what that gives us.
Yeah, that's a good point. So I think of this file system as effectively your working set for performing the build or performing the tests, running the test suite, doing the Docker build, and so on. For context, as I said, the VM file system image itself is fairly massive because it has to contain all these like runtime dependencies that your CI jobs probably rely on. But on top of that, compiling a large project, like if you were compiling the Postgres repo, just the code compilation itself needs a bunch of disk, a bunch of memory. we'd categorize this as like purely ephemeral working storage for your CI jobs. And that's also part of what our system configures. So based on the size of the VM that you request, we'll make sure that one, the host machine that's going to adopt the job has enough spare disk to be able to accommodate the job. And second, the copy on write clone that we construct for this VM, we ensure that it has enough capacity to only allow X gigabytes of write and no more. Another sort of neat optimization that we can do, because we don't care about durability, is we can kind of disable flushes entirely. So for context, a lot of database systems rely on the fsync syscall to flush pages to disk, and that's a very important guarantee to guarantee durability in a database system. But for CI, again, because we don't care about this like working storage after the job is done, you actually want to make the opposite trade-off. You actually want to buffer up as much as possible in the kernel before you try to write anything to disk. If possible, you actually want the entire thing to be buffered in memory and never flush to disk if you could. Right. So we have a number of optimizations that really help with code compilation performance because of the fact that we're very loose about flushing to disk. We'll buffer up as many pages as we can before we flush to disk at all.
And that's the power of solving really specific use case, right? Like you get to understand what use case you're solving, and then you can optimize for that specific use case. So if you didn't have the idea of, you don't really need the durability, you wouldn't have, let's say disabled fsyncs or wouldn't flush and so on. That's really interesting. Just a question around, how did you identify that this is a level of optimization you always wanted to do, or you identified this in the process of implementing this?
So it was definitely the latter. But what we were taken aback by was we started the hardware kind of thesis around the business by recognizing that a lot of code compilation is actually firstly single core bottleneck. So the intuition behind this is for single core runtimes like Node.js, Python, it's only ever running on a single thread. So single core performance just is kind of the main bottleneck in terms of CPU bound workloads for those. But surprisingly, compiling large code bases turns out to be both single core bottlenecked as well as bottlenecked on IO, which is the latter part of it is not something we anticipated before. I think in order to kind of gain intuition around that, we should talk about what really sort of happens when you compile a large piece of code. If you have a large project with a large project is effectively like a dependency graph of packages, right? You have some packages that I would call like strongly connected, like a utilities package that's being used by all of your different subsystems in your code base. But then you have sort of these leaf packages that no one else really depends on, but the leaf packages themselves effectively depend on your entire project hierarchy. Code compilation is effectively serialized based on the nature of this like dependency graph, right? Like if you have package A that depends on package C, which depends on package B, you have to compile them in reverse order, because for A to resolve its symbols, it needs to have access to object files from the previous dependency packages. And we realized that for most projects, building a lot of these large projects on a 32 vCPU VM doesn't actually make it that much faster than building it on like an 8 vCPU VM, because you're effectively sort of bottlenecked on the nature of this dependency graph and the single core performance of those VMs. And secondly, during the compilation itself, you're reading source files, you're parsing them, you're generating these object files. After these object files are generated, the linker effectively, finds all the symbols in each of the object files, figures out where those symbols are defined, and at the end of it, puts all of it together into a executable, a single binary. This linking process is extremely hard to parallelize. Like the linker is effectively like a sequential job. But in the midst of all of this, because you're constantly reading all these source files, you're writing object files, the linker is trying to jump around a bunch of these object files to resolve all these symbols. Code compilation ends up just being like extremely IO bound as well. So hopefully I've like given you some intuition around why it's not only sort of bottlenecked on single core performance, but also on just like IO, just because of the amount of times you're reading and rewriting object files and trying to put them all together, trying to produce a single binary at the end of all of it.
Very interesting. And that makes sense. So when I never thought about this, to be honest, but when you explained it, I was like sort of creating like a mental model, like how things will be happening, and it's a bit more clear, like why it would be bottlenecked on single core performance and also IO. So that does make sense. The other point that you mentioned was about using like gaming CPUs. Why gaming CPUs? And let's go a bit of understanding what they give you, and both in terms of cost and performance and so on.
Yeah, so a bit of like history here is that I'd say even 15 or 20 years ago, there were particularly large differences between the platforms that sort of the hardware motherboard platforms that were meant for desktop use and the motherboards and the CPU platforms for server chips. Primarily, these differences were about how many PCI lanes these platforms have. What that meant was server CPUs allowed you to attach higher performance network cards, which is very important in production server environments. They would allow you to attach more high performance storage cards. They allowed a lot more extensibility than consumer grade hardware. And primarily, they also actually supported error correcting memory. So for the longest time, you could only attach ECC memory to server CPUs, and desktop CPUs just like did not support them. Over the years, however, the platform support for these kinds of things has like more or less converged. You can now attach error correcting RAM to desktop CPUs. For example, the latest AMD Ryzen chips at the platform level support the latest PCI generation. They support error correcting memory. However, the competition in kind of the consumer desktop space has only heated up, and kind of the main access for a lot of consumer desktop use cases like gaming, a lot of those applications turn out to also be bottlenecked on single core performance, which has caused which has caused the vendors, primarily Intel and AMD, to push very hard on single core performance. High single core performance or best in class single core performance is one of the reasons Apple's M1 chips have done so well, or Apple's M generation of chips have done so well for laptops. I think a bit of intuition behind this is that in most desktop use cases, and also in gaming, you kind of have a main thread that kind of drives the game loop. A lot of background operations like physics simulations are actually offloaded to your graphics cards, to your GPUs. So while modern games have gotten better at utilizing more cores, inherently video games are still sort of bottlenecked on single core performance. So you kind of combine the confluence of all of these like factors and kind of market forces. What's happened is consumer chips have skewed towards fewer cores, as in your MacBook only has typically 10 cores, and even high-end desktop chips only have 16 cores, 32 vCPUs. So they've skewed towards fewer cores but higher performance cores. Whereas server hardware has always skewed towards more parallelism, being able to handle most requests parallelly at the same amount of time. And so server chips have skewed more and more towards higher core counts. Server chips having higher core counts also allows cloud vendors to slice them up in various ways. If you have a chip that has 96 cores, that gives AWS a lot of flexibility in terms of how it can slice that up in various ways to serve various kinds of workloads.
Interesting. And does it tie back to the point that the CI workloads are also typically that, right? They are bottlenecked on the single core performance. And when you get better single core performance, because, hardware industry has improved in that sense, you kind of reduce the bottleneck, right? And you anyway do not get any, parallelizable workloads, or let's say minimal parallelizable workloads where you can actually do things in parallel. I think it makes sense. So again, like really focused on this use case, it makes sense. That is cool. And in terms of cost also, does it gives you some advantage in terms of saving some cost and providing better cost features for the users?
So I'd say for the most part, it is more expensive per vCPU, just in terms of like the cost of the hardware itself, the cost of the CPUs themselves. It is more expensive per core to run a consumer desktop core as a vendor like we are, than it is to run a server CPU core. But the interesting thing about that trade-off is that the cost differential there is less than the perf differential between the single core performance of a consumer CPU versus a server chip. And in our case, because our customers are paying based on like a usage based billing model, if their CI jobs run faster, they're actually spending less money. So not only are they, winning in terms of developer productivity and letting their developers get their work done faster, they are actually spending a lot less. That's kind of another reason why CI is like a very unique class of workloads. If you were running a production workload like serving a database, what I just mentioned just doesn't apply. Like you can run it on like the fastest core on the market, but it's not really going to meaningfully reduce your total cost of operations. In fact, a lot of production applications are not very CPU bound, right? Like it's hard to contrive a scenario where something like a database system or a web server is actually bottlenecked on CPU. It's typically storage and IOPS, which is why the recent Planet Scale Metal launch like went down so well, because IO latency and IOPS are kind of the main bottleneck when you're serving a database, not the CPU.
Fair enough. Yeah, that makes total sense. Let's take a step back, right? So let's say I've been successfully using Blacksmith, and I share it with my friends, and you have more users now. And they also start using Blacksmith. How do these events get distributed? Let's say partition, and so such that the workload is evenly distributed. What happens at that level? And so I have more questions, but I'll ask them after this.
Yeah. So this goes back to like the initial kind of point I made about why CI is like a serverless workload, and as a vendor, what that kind of looks like on our side. So one customer pushing code at the same time as another customer means that as a vendor, Blacksmith has to provision capacity to handle peak usage thresholds across our entire fleet. So if we have 5 customers that are pushing code at the same time, our capacity planning needs to account for that. However, when you get to a scale of like 300 customers or 500 customers, 1,000 customers, each with, let's say, an average of 20 engineers, across 20,000 engineers, the probability that all of them would push code at the same time sort of exponentially decays. Right? And that's kind of the beauty of running a multi-tenant system, that our unit economics and our capacity planning becomes a lot more predictable and gets easier and cheaper as we hit higher scales. Another way to visualize this is that as we scale and have more developers pushing code on the platform, our peaks or our P99 utilization levels get compressed down, and they get closer and closer to our average utilization levels, because no single customer or no single developer can perturb the usage curve too much to make it make a difference. I think the second part of your question was about how we ensure that things are distributed in a way where we can maximize utilization. This is also where I think it's worth highlighting why a traditional hyperscaler-based architecture, like running a CI Kubernetes cluster on EKS on AWS, is perhaps not the right fit for CI as a class of workloads. And the intuition behind that is the following. Traditionally, Kubernetes clusters and pods inside of a cluster are scheduled to maximize availability. Kubernetes will by default not pack pods onto the same physical host machine. You want, the entire point of running multiple pods is you want redundancy. So you don't want a single node's failure to kill your entire service, which means Kubernetes will try to spread your pods across many nodes and many zones by default. And for CI, you actually want to make the opposite decision. If you have a fleet of 100 machines, if you're an org that is operating a Kubernetes cluster for CI with like 100 machines, but you're only running 100 CI jobs that may not necessarily need the entire capacity of the cluster, you want to pack these jobs into the fewest amount of nodes as possible. Like if you can pack 100 jobs onto a set of 8 machines, you actually want to do that packing, and you want to auto scale your cluster down so that you're not paying for all this like idle capacity. And with the approach we've taken, we have full control on how these VMs are scheduled. So we can kind of effectively bin pack these workloads onto the fewest machines, which means we have a ton of like idle capacity to handle bursts in larger jobs. And this is all sort of work that pops up at a company with more than 100 engineers, but it basically requires a full-time team to maintain all of this infrastructure, to make sure you're not spending too much money wastefully on idle compute for CI, while at the same time ensuring that when your developers push code, compute is actually instantly available.
And so, what role does Firecracker play here in terms of the isolation that it provides across different jobs?
Yeah, that's a great question. So the reason you want to run a multi-tenant system like ours on Firecracker as opposed to just running vanilla Docker containers is there's two main reasons, but from the vendor's perspective, from our perspective, is actually just the fact that each Firecracker VM gets its own kernel. When you run a Docker container or you run 5 Docker containers on a host machine, they all share the host's kernel, which is a big security boundary that you do not want to cross when you're running a large-scale multi-tenant system. Because each Firecracker VM gets its own kernel, there's effectively no way to escape the sandbox of a micro VM. Whereas in a traditional container setup, if you were running untrusted workloads, the only security boundary between the containers and the host operating system kernel is it can be violated by one vulnerability or one bug in that layer, whereas VMs provide a much higher level of isolation. So that's kind of on the security side of the aisle. But we also isolate these VMs across 3 axes: CPU, network, and disk. So for a VM that only requires 2 vCPUs to run a small lint job of some sort, we'll use C groups to isolate their CPU utilization to that. We will apply additionally an IO throttler, where when these VMs need to use up the IO, they get access to the underlying host's full capacity, but that there's some fairness across VMs when a lot of them are trying to use the host's underlying IO at the same time. And as I mentioned before, they're all sort of in their own network namespace, in their own private subnet. They're not allowed to serve any traffic to the outside world, but obviously they can hit external destinations, and we can provide a lot of out-of-the-box monitoring for a lot of these things as well.
Very interesting. When you were introducing the features and the benefits of using Blacksmith, you also mentioned that the current setup that we have, there's a lot of flakiness. So I have 2 questions there, right? What adds to this flakiness in terms of the CI workload, and how do you deal with that to avoid the flakiness?
Yeah, this is also a great question. So I'd categorize flaky tests or flakiness that developers typically see in CI into sort of 2 buckets, right? There's flakiness that we'd argue is a real problem that needs to be fixed in the tests or in your code base, right? You genuinely have a non-deterministic system, and a unit test is highlighting a real bug because the system is sort of correct 99% of the time, but not correct that extra 1% of the time. And this was fairly common during my time at Cockroach. Because it's a distributed system, we spent a lot of time writing these concurrent tests that we'd stress in CI on every pull request for 15 to 20 minutes, just because there was no other way to ensure that we've shaken out all the non-deterministic failures in these tests. But I'd argue that that's sort of the good class of flakiness because it's highlighting a real problem. Or if in the same way, if you have a unit test where it may not be highlighting a real bug, but due to timing issues in the test itself, the test itself is flaky, even though the code being tested is correct. And this you see fairly commonly in end-to-end browser tests. So with things like Cypress and Playwright that simulate an entire web app, you'll see flakiness when the Playwright runtime expects a pop-up to show up when an event occurs, but the pop-up occurs after some kind of a delay. Those are real issues that developers need to spend time fixing. However, the second kind of more pernicious kind of flakiness is what I'd call infra flakiness from your CI infrastructure. And we've I'm sure we've experienced that kind of flakiness a lot throughout our careers as well. But that primarily happens because your CI jobs are running on a compute fabric that is not well provisioned for that test suite, right? So just as an example, at one of my previous jobs, we had a test cluster abstraction that all of our unit tests would spin up. And it was spinning up effectively an entire CockroachDB cluster in memory. At peak business hours, when a lot of developers were pushing code at the same time and all of their CI jobs were getting scheduled on our finite set of agents at the time, these sorts of tests would often flake and time out because They're sort of heavyweight. They're running a lot of stuff just to do the setup. And then by the time they are able to set up the test harness, the test is actually timed out. I'd argue this is more pernicious, and this is exactly part of Blacksmith's value prop. Because we're giving you access to sort of the raw hardware, um, we're not setting these VMs up with EBS volumes that throttle IO. We're also giving customers visibility into the resource utilization of their CI jobs. So, for instance, if you're running a CI job on us on a 4 vCPU instance, we'll tell you if we think that instance is too small to be running that test suite. I don't want to say too much about what we're doing for the first, what we're gonna do for the first side of the aisle, but we think there's a lot of product to be built to help developers not only with the second more pernicious kind of flakiness, but also help them resolve structural flakiness in their code base or in their test suite.
That's so common, to be honest, right? I have seen pipelines failing with no feedback at all, like why certain thing fail, and then you would just retry. If you have time, it's not a problem. You can wait, you can go for a coffee, go for lunch and whatever, come back and it's passing. But when you don't have time, when you're making like quick fixes to production, and if it fails for random reasons that you don't have any control on, it's really painful. So I totally understand that. And I think the usage of, the control that you have on your hardware, I think gives you that ability. And that's really powerful. You mentioned that you give feedback in terms of the resource that my CI job would require, right? Like, what does that feedback look like? Is it like some sort of logs, some sort of events that I get back?
It's literally as simple as letting you view your disk IO utilization across the runtime of the job, your CPU utilization across the runtime of the job. This is sort of still in the works, but we're also going to help you correlate a specific step in your job that perhaps timed out with the CPU utilization at that particular instant in time. So that helps you either confirm or invalidate the theory that the job might just be running out of resources. And yeah, you're right. We've all seen a lot of these flakes, and the other pernicious effect that this has on the entire team is that it reduces your trust in your smoke test test suite. I've been at internships and previous employers where after a deployment went out, they would run a pretty comprehensive smoke test against the production instance. Oftentimes, that smoke test would be extremely flaky, and the person who was on call would be in charge of spending an hour or 2 hours almost like every day trying to understand whether any of the failures actually matter and whether any of the failures are worth looking at. So it sort of defeats the point of having a smoke test to begin with if you can't trust the outcome. And we think all these productivity bottlenecks are only going to grow with an incoming explosion in the amount of code that's going to be written with AI code gen tools. So if we buy that there's going to be that explosion, then the world needs a piece of compute fabric that can run these CI workloads, that is built from first principles for these kinds of workloads and isn't burdened by product SKUs on the hyperscalers.
I totally agree. Like, the signal to noise ratio is really important. If you're just getting too much noise at the start, you will probably go deeper, try to investigate. But when this happens in a repeated manner, you just say that, oh, it's just noisy, which means that you might also be ignoring some signals, which means that you might also be ignoring some of the problems in your system. And that's a big problem. You mentioned observability, right? Like, you can give the users a hint about what step is failing, what was the CPU utilization, memory utilization, and other stuff. So basically, you're giving the users enough observability in terms of how they can probably address or by increasing the resources. And this is one example, right? Like increasing the resources or something like that. What are other examples where observability would be really useful, where the users have to have the control to basically change something?
I think one use case that we see quite often with our customers is when a job fails, being able to immediately SSH into that VM itself and inspect the state of the VM. Right? Like you have, let's say, an hour-long job. Somehow the failure only reproduces in CI, but not on your local machine. Like we've all experienced scenarios where it works on your local machine, but it flakes in CI. We don't have tooling for this yet, but this is something that's sort of in the works to allow developers to easily set thresholds where we will actually pause execution after a step that fails and open up an SSH server where they can jump into the VM, inspect the state of the machine, and figure out why the flake occurs in CI but not in their local dev. I'd say that's one of the more like common tasks. I think in terms of like use cases for observability, one thing that doesn't quite exist in the market that we'd want to attack at some point is benchmarking of your code, right? So this comes up a lot when you're building a performance critical system like a database or a language runtime, where you have some of these extremely hot code paths. Imagine, the code path to perform a select query in a database. Any regression in that code path is going to lead to effectively an unacceptable regression in the performance of your database. However, in most of these systems, there's no way to ensure against these regressions in CI. The way a lot of these things kind of work in practice is the person who's the area expert on that part of the code has to very, very strongly scrutinize your code, make sure that you're not performing any new memory allocations or you don't have a misplaced log line somewhere, to make sure that you're not going to regress the performance of the entire system with a tiny patch. So that's an area we're quite interested in exploring. And it's also an area that's hard to solve on the existing hyperscalers, right? Because these are nanosecond to microsecond precision benchmarks. Running such high precision benchmarks on run-of-the-mill EC2 instances ends up being quite noisy, because EC2 instances are not single tenant. You don't know what else is running on the physical box that's running that EC2 instance. So you effectively need some way to run these like single tenant workloads where the orchestration system like Blacksmith guarantees that that's like the only VM running on that host. So that's an area we're interested in exploring.
Very cool. In terms of observability, right? Like what kind of integrations do you already support or plan to support? For example, I have some, profiling data or some insights about my jobs. How can I take it somewhere else and, have these visualizations, look at the trends and so on?
So this is an interesting product question that we've talked about ourselves. At the moment, we don't have external observability integrations. We have thought about building one that allows customers to easily, exfiltrate their CI logs into their large observability provider, like a Datadog or New Relic. But another direction that I think is a lot more compelling is for Blacksmith to sort of become your statement of record for all things CI observability, where you can tell us which pipelines are deployment pipelines that you want to be alerted on when they fail. Or if a new deployment has not gone out in the last 2 days, maybe the person who's on call wants to get paged about it. So a lot of these observability integrations are on the way. And I think the cases where it makes sense to have us exfiltrate that observability into an external system like Datadog, we're also going to work on cases like those.
Sounds good. I'm talking about the future. I know you've already mentioned some of the use cases that do not exist yet, but you have been, planning. What are like the really soon incoming features that you can talk about, of course?
So an area that we're quite excited about is providing ephemeral compute for autonomous coding agents like Claude Code or any of these agents. The intuition behind that is all these autonomous coding agents are very iterative. So they need a fast feedback loop and a high quality feedback loop for them to validate their changes. Now, this is fine if you're on a relatively small code base at young startups where everything builds and tests locally on your MacBook and it's all good. But this is effectively impossible at companies that are beyond a certain size. Most large enterprise code bases are effectively untestable on a single local machine. So one of the areas we're quite excited about is how do we give these coding agents a fast and high quality feedback loop to iterate on their changes in a way that doesn't take over the developer's local laptop, and an environment that sort of comes baked in with all of your CI dependencies. So that's an exciting area. And as I mentioned, we're going to keep pushing on a lot of out of the box observability improvements, because we think like that's sort of the more immediate battle for developers. When writing code becomes much easier, more than half the battle will just be getting the code merged in a way where you can be confident about your changes.
Very good. Well, I think we have covered a lot of details about how everything works, and I'm sure there are so many things are going to come up. So I am excited to learn more about Blacksmith going forward. I'll keep following the updates. But yeah, thanks a lot for joining me today and sharing all the amazing insights. There are some of the really good insights that you have given from the CI workloads that I'm really curious about. So if you want to share some references that have helped you building Blacksmith, understanding the CI workloads better, I don't know, some benchmarks, just feel free to share it with me so I can attach it to the description so viewers can learn more. But yeah, looking forward to learn more about the upcoming features.
Sounds good. Thank you for having me. It's a lovely conversation.